Hey guys, today we're talking about Lelantus-mw, which is currently live on the Beam mainnet. So we're going to talk about exactly what it is, what it does, how it works, and what it means for Beam. So we start where every blockchain discussion starts, which is Alice and Bob. So I like to say that Alice is actually Bob's personal FBI agent. So when Bob withdraws some cryptocurrency from an exchange, Alice can see Bob's address. If Bob sends some cryptocurrency to Carol, let's say some Bitcoin, and then Carol deposits it right back to another exchange, well, Alice can see Carol's address as well. And then it's very easy for her to see the link between Bob and Carol on the blockchain. So it's this link that we're going to be focused on today. Of course, Bitcoin's method of hiding this link was pseudonymity. As we saw, that is very easily broken with KYC. The next best solution is decoys or plausible deniability, right? So this is what Mimblewimble does. This is what Monero does. And basically here, it looks like Bob sends his coin to 11 different addresses. And assuming that those are 11 believable addresses, right, that it's plausible, the chance that Carol is Bob's intended recipient is just 1 out of 11. And of course, that probability goes down as you increase the number of decoys. However, as we'll see, this is quite easily broken with graph analytics. We'll talk about that in just a minute. What we'd really like is just for a coin to basically like disappear from one part of the blockchain and then reappear somewhere else without a link between those two places. This is what Lelantus-mw does. And the name Lelantus actually comes from a Zcoin implementation. So Zcoin designed, the folks at Zcoin designed Lelantus, the Lelantus protocol, and Beam just talked with them and took the idea and made some adjustments and did their own implementation specifically for Mimblewimble. But it's got the same unlinkability as the Zcoin version. Sometimes this is called shielding or burning and minting in the case of Zcash, but at a high level, the idea is the same. Before we dig into it, though, it is important to remember that any kind of system like this is limited by the quality of the anonymity set and by metadata. So we can imagine that if Bob withdraws, let's say $914 from an exchange, and then he uses the most private blockchain in the world to send it to Carol, and she deposits it 4 hours later, $914, Alice will connect the dots, of course. So let's take a look at this in action. And we're going to be comparing a base Mimblewimble transaction to a Lelantus-mw transaction at several different levels of depth to see exactly what it does and how it works. Before we talk about the transaction, let's talk a bit about the broadcast phase. So every block in Mimblewimble is essentially a big coin join, right? So Bob's UTXO input from the exchange is mixed with all these other inputs, and Carol's output is mixed with all the other outputs. So Beam has an extra layer of privacy added at this layer in case of a sniffer attack. So what is a sniffer attack? Before Bob's UTXO gets coin joined and broadcast to the whole network, it's shuffled around the blockchain randomly between different nodes so that the coin joiner doesn't know Bob's IP address. So during the shuffling phase, an attacker could potentially see Bob's transaction before it gets coin joined. So then they would have the explicit link between Bob and Carol. To deal with this, Beam uses decoy outputs and adds them during the shuffling phase. So in order to be forwarded on, this needs to have a minimum of 5 outputs. And Beam will just keep adding decoy outputs until it gets to this number. So those same decoys are then later used as inputs. So this makes things even more obscure, and it makes sure that we don't have these outputs just hanging out on the blockchain indefinitely. Here's a view of 3 different blocks in the Beam Explorer. So in the first one, Bob withdraws from an exchange. So this is an input that Alice knows about. In the second one, he sends some Beam to Carol, and then in the third one, Carol deposits back to an exchange. So in a base Mimblewimble transaction, Bob's input to Carol links back to his output from Alice. And let me move myself out of the way here. You can see this. So In that transaction, there are 7 inputs, and one of them is Coinbase, so that's obviously not Bob. So that means that each of these transactions, each of the transactions connected to these outputs, has a 1/6 chance of being Bob, right? And then by the same logic, each output here has a 1/7 chance of being Carol. So if we take Alice's perspective, the probability that this input is Carol is 1 out of 42. Right. In a Lelantus transaction, now, Bob doesn't create a UTXO to send to Carol. He deposits his coin to a shielded pool down here. And likewise, when Carol spends it, she doesn't reference an old UTXO up here. She just references a range in that shielded pool and then a spend proof that says, I'm spending a valid coin in this range. All right? And that's it. So if you look at this, we see that the shielded pool in this example only has 9 elements. That's because this was taken literally hours after it was launched. This is a real transaction, by the way. Okay? It is designed currently for 2 to the 16 anonymity set. So that means that you have a 1 out of 65,000 chance for each transaction of being, any given person. So we'll see some restrictions that apply to this in the next slides and how to use it correctly. But that's what to think about. And the magic here is that in order to spend, Carol doesn't need to link to a previous UTXO. She just links to a range in this shielded pool, which everybody knows about, and says one of these is mine. And that can be a range of up to 65,000. Here's Bob's transaction to Carol shown a little bit differently. So remember, we have 4 inputs. One of them is Bob's. Let's say that Carol knows exactly which one is Bob's, all right? And then we have 8 outputs. One of them is Coinbase. The other 7 are equally likely to be Bob's intended recipient. Let's say that instead, Bob sends a transaction to himself first and then sends it on to Carol. So what is the probability that Carol is Bob's intended recipient now? It's 1 out of 42 if you count the little dots. But really, if we say that each transaction has an average of 6.5 outputs, which is about right, then it's 1 over 6.5 to the power of the number of intermediary transactions. So in this way, the privacy kind of increases exponentially with each transaction. All right, let's look at it the other way though. Let's say that Carol is not Bob's intended recipient. What is the probability of Carol randomly ending up in this anonymity set? Well, if we just use as an example 1 million active Beam addresses, the chance of hers being chosen would be 42 out of 1 million. So it's very unlikely that Carol will randomly show up here. So what if Bob and Carol are linked twice? Then it's this low probability squared, right? So for every time that Carol appears in one of these subsets, it's extremely unlikely. So that every time it happens consecutively, that's even more and more unlikely. So in this way, the privacy decays exponentially. All right? With Lelantus-mw, when used correctly, which again we'll get to in a second, the probability of anything happening, regardless of the number of intermediary transactions, regardless of the number of the transactions between the same 2 people, is 1 out of the anonymity set. And as we said, that's up to 65,000 with the current design. So in a mw transaction, Alice's UTXO gets removed from the UTXO pool, and Bob's gets added to the UTXO pool. And then we also have this kernel added with no value. Instead of the public and private keys that we have in Bitcoin, we have these essentially a secret value, which Alice knows, which she can use to create a transaction. And in this case, that's this K1 value. So because Alice knows K1, she can create K1G, which will create a balanced transaction on the ledger, right? So in terms of validating this input, this is valid because it's linked to an old UTXO that was already approved. That output is valid because these V's balance out, and that's done with ECC cryptography. By the way, let us know below if you want to see a video on ECC cryptography, because we could totally do that. And then finally, we need a bulletproof to prove that neither of these are negative numbers. So we're not creating new coins, right? So what does it look like to create a shielded output and then use a shielded input? Lelantus is implemented in primitives. So these are going to live side by side with these Lelantus primitives on the Beam blockchain. So Bob removes his UTXO just like a regular transaction, but he doesn't add anything to the UTXO pool because Carol is not going to reference the UTXO pool. Remember? The information that he would have used there is going to get combined with the kernel and added to the shielded pool instead. So let's look at this real quick. Here we have two K values, right? The K value from Bob's would-be output and the K value from the kernel. And these are just added together for the shielded commitment. The V, or the value, carries from the would-be output, right? So this V has to balance with this V in order to get validation. And then the S, this S appears in the kernel and is carried forward. And this is the serial number. Alice is going to use this serial number, or excuse me, Carol is going to use this serial number later to prove that she has a valid, to prove that she's spending a valid coin, okay? And what we get here is a double-blinded commitment. So this is something that is unique to Lelantus. It also shows up in the Zcoin version. Normally, we have a single blinding factor with our value. So a single blinded commitment. Here we have our blinding factor and then also this serial number. So we have a double blinded commitment. These other functions of Mimblewimble perform in basically the same way, right? So Bob is linking back to this one to gain legitimacy. Bob's able to create a balanced transaction, and then we verify the transaction in just the same way. Now, the bulletproof has to be performed on this shielded output. And as we just said, this is a new type of primitive. This is the double-blinded commitment. So we need a slightly different bulletproof, but it's not really a big deal, okay? And the Zcoin folks figured out a bulletproof for Zcoin, and the Beam folks have figured out a new bulletproof for the Beam blockchain to handle these double-blinded commitments. Now, let me move myself over here like I forgot to do in the last take. When Carol spends the Lelantus as an input, let's take a look at this, okay? So remember, she's not going to remove anything from the UTXO pool, but she will add one for whoever the recipient is here. The would-be input is taken from a range of the shielded pool, okay? So we still need to have, Carol still needs to have some commitment or something to prove against. And this is going to be pulled out of the range. Carol is going to create a spend proof using this S and the information about the old transaction. And then the blockchain is going to use the spend proof together with the UTXO, her public key here, which is these K values, and this range. And this spend proof will just return a big thumbs up. So this is something to notice that's different here, right? So with a Mimblewimble transaction, the validation happens through linking and ECC, and then there's also a bulletproof. In a Lelantus transaction, the validation just happens by a yes or no out of this spend proof. And the spend proof, that one yes or no covers all three functions here. So it's going to say that the V is valid, the inputs equal to outputs, and none of them are negative. Okay, so something that was very important to the Beam implementation here was that the public key, or basically the information that is revealed publicly in order to validate the transaction, is the same type of information. It's K values, right? So it's the same type of information as in the past. And what this allows basically is for this to just coexist very peacefully and workably with base Mimblewimble transactions on the same blockchain. Okay, let's look more closely at the spend proof. Now, remember that the purpose of the function of this spend proof is so that Carol can create a new UTXO out of thin air, right? Without linking back to a previous UTXO. So to create a proof, a spend proof, first she inputs the output that she wants to create, right? So we said, I think that was a deposit back to an exchange. She includes her public key, which is the K values of Bob's commitment, right? Her private or secret or spending key, which is the serial number, and then a range, right? So this creates a spend proof. And anyone can use this spend proof together with her UTXO, which will be posted on the blockchain, and her public key and that range to get a true-false value. And what this says basically is, for this UTXO and private key, one element in this range opens to 0. What does it mean to open to 0? Okay, well, so down here we have our shielded pool, which is full of double-blinded commitments just like this, right? So this one happens to be from Bob, which is the one that Carol wants to spend. The prover element, or the prover algorithm, right, is going to take each element in this range, and remember this can be up to 65,000 different commitments, and it's going to subtract some values from each one. First, it subtracts this information that Carol provides, right? So this is her UTXO up here, and this is her secret key. And after that, it's going to subtract some more publicly available data, okay? So this is Carol's public key down here, this KS plus here, and then this is from her UTXO. And if all of this is correct, the answer down here will be 0. Well, let's go back through. So we have this S value, which is canceled out, subtracted. We have this V, which is also subtracted. K sub C is, you know, canceled out this way. And then here's our K sub S and K at Mimblewimble over here. So yeah, it opens to 0. So when Carol creates the spend proof, she does this first one and then leaves the result on the blockchain so that anyone can come along and do this second one, and it should open to 0, right? And this process is nothing new. It's called a Sigma protocol. In fact, the smallest unit of Beam, called a groth, is named after the author of that paper. What is new is that we can scale this logarithmically, right? So Lelantus makes it possible to validate Carol's transaction against 65,000 others in about 1 second. And additional outputs can be verified against the same anonymity set in only 10 milliseconds. So this right here is the big technical achievement behind Lelantus. And this work was done mostly by Aram Hivanyansan over at the Zcoin team. And I actually have a video with them as well if you want to check it out. But the idea was then, you know, written down in the white paper, and then the Beam guys saw it, and then they had idea for how to use it with Mimblewimble. And so it was, you know, implemented separately for Beam. There are a lot of other features that are also going live at the same time, and one of them is non-interactivity. So this is when Bob and Carol can do a transaction without having to interact, right? Okay, so in Mimblewimble, this K sub C value is essentially Carol's secret, right? It's the secret that she needs to use in order to create a valid transaction in the future. But of course, Bob needs this value in order to create a balanced transaction here. So, you know, if Bob knew this value completely, then he could spend it before Carol does. So we have this interactive process, right, where Carol creates kind of half of a secret and gives it to Bob, and then uses the other half of the secret to spend it later. And it requires this back and forth directly between Carol and Bob. Alternatively, and this is what Beam has done now, so this is live on the command line wallet, and it should come to the GUI wallet soon. Carol is going to choose a new public and private key pair, okay, and then give her public key to Bob. Bob will choose this random K sub C value, you know, his device will, so that he doesn't know it, but it will be encrypted to Carol's public key. All right, so we've got Bob's message, It's encrypted by the public key. Carol can use her new private key from this key pair to decrypt it and then use it as a future input. Okay, but Bob still needs to send this encrypted message now to Carol. The way that we do that is it's embedded in the bulletproof. All right, so this is something that you can read into this more if you want to. And again, let us know if you'd like a video on this. But there's basically a degree of freedom here in the bulletproof so that we can add a number to it, and then after it's been published, do some tricks and get that same number back out. So Bob is going to just embed this message in the bulletproof so that when when Carol looks at the blockchain and looks at all the bulletproofs that are posted, she can see that there's one which contains a key for her, and then she'll use her, her new private key to unlock that, and then take the K value and use it here to create a new transaction. Okay, so that's how these non-interactive payments work on Beam, and you can check out the white paper if you'd like to dig deeper here. Finally, and this is the last feature we'll discuss, Beam also now supports confidential assets. Anyone can mint a new token on the Beam blockchain, and all these tokens can use the same anonymity set because there's nothing publicly available that says which kind of token they are. Okay, so there's a new field called Asset ID, and the default value for this field is 0, which of course indicates Beam, the default asset, is being spent. If we look at the blockchain here, every time there's a V or some value being transacted, there's also an H value. And this H also has a degree of freedom, just like we saw in the bulletproof. So it's possible to embed a value into this H. So that's what we do. So we also need a proof which says that our asset ID is valid, that it's basically on the list of created assets. And so that's called an asset surjection proof, excuse me. And that goes down here next to the bulletproof. And again, anyone can create a new currency on Beam. This is done with a special kernel. Remember that kernels are not cut through, so it makes them a good way to store kind of long-term data on the blockchain. So every time a new asset type is created, it needs an owner, some metadata like its name, and some Beam to be locked up. Okay, so this is just to ensure that the network resources aren't wasted. And then the system gives it a unique asset ID. So the asset owner is then allowed to mint new coins, and it does so with another special kind of kernel called an asset emission kernel. And then anyone can destroy a coin after they receive it just by sending it back to the originating kernel. Okay? So after 100% of the issued coins have been destroyed, the owner can optionally kind of choose to shut down the currency, and then they get back the Beam that they deposited originally when they created it. So this is how confidential assets work on Beam. Now, what are the practical considerations for this current Beam implementation of Lelantus-mw? So first of all, the transaction size is significant, all right? And unlike a mw transaction, it cannot be cut through. So it's intended as an add-on feature. It can be used on demand when you need extra privacy, right? So also the number of shielded transactions per block will be limited, and we'll just have dynamic fees in order to make sure that this is fair, right, and accessible to those who need it. Next, we know that when there are multiple transactions, there are huge gains in efficiency. Remember, the first proof takes 1 second, and every following proof with the same anonymity set takes only 10 milliseconds. So as much as possible, we would like all the shielded outputs in a block to use the same anonymity set. However, the designers expect that there's going to be thousands or maybe even tens of thousands shielded transactions per day. So there would only be 65,000 new shielded transactions about every week or 2 weeks. So if your anonymity set is the most recent 65,000, it will only work with shielded outputs that are less than a couple weeks old. Remember, just as we saw a few slides ago, if our anonymity set is a random subset rather than the most recent, then we've got those hardening links with every subsequent transaction, right? So we don't want to do that either. So the solution that Beam has come up with is pretty ingenious, actually. So by default, the anonymity set is the most recent 2 to the 16 shielded outputs. Or again, that's about 65,000. If you can use this anonymity set, you don't need to worry about recurring transactions. This is what I've been referring to all along as the correct way to use Lelantus-mw, is to be among the 65,000 most recent transactions, or shielded outputs. So there's a bit of a penalty then if you miss the window. You can't use that default anonymity set, so you're allowed to create your own with up to 1,000 different elements, right? Or a range of up to 1,000 instead of 65,000. But this isn't really a big deal because you can just turn around and do another mw transaction, and this one will have the full 65,000 privacy set. So if your shielded output is more than 2 weeks old, there's just an extra step of creating one with your own subset and then creating a second one with the new anonymity set. Okay, so that's it. Thank you guys so much for watching. Let us know down below what you enjoyed, what you didn't enjoy, what you'd like to see next, what you'd like clarification on. Make sure to check us out on Twitter, visit our website, and you can check out me on Twitter at Hawkins, and I'll see you guys next time.